Math 230, Quest to College. I'm Joe Vasta, and this is the review for Exam 5. We'll call this Review 5. This covers Chapter 7, Probability. So if you haven't done those review exercises in the book, you might want to do them before you look at this video. But before we get going with the review exercises, I have 5 puzzles to look at. And after that, we'll get going with the problems. Look at this. My very educated mother just sent us 9 pizzas. So what's up with these? Homes, can't, I'm no wimp. Washington's army jogged many miles and jogged very hard to Philadelphia. To find pretty British ladies, Johnson gave Hayes garish and clever heart-shaped clay maps. It almost doesn't really make sense. But what's up with these 5 things? And at the very end, we'll figure that out. The review exercises from Chapter 7, if you have not done them, you might want to try to do these things on your own. That's the best way. Or you might just be watching the video, pause the video, and see if you can do the problems as I do them. So here it goes. A box contains 3 red marbles, 4 green marbles, and 2 yellow marbles. So red, 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 green, 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 and then yellow, yellow. So it looks like we have 9 marbles in the box. What is the probability it is green? Okay, so you draw 1 marble from the box and you want to get a green marble. Where probability is what you want over what's in the box. And that was my informal definition. So what I want is a green, and there are 4 green marbles out of the number of marbles in the box, and there are 9. So 4/9. Our fraction does not reduce, so that is our answer, 4/9. Okay, so that's kind of how probability began. So with the first several problems in this review, we'll have the same situation where a box contains 3 reds, 4 greens, 2 yellows. So let's move on to the next problem. Okay, so I have 3 reds, 4 greens, 2 yellows. You draw 1 marble from the box. What is the probability it is not white? Okay, so non-white or not white. How many non-white marbles do you have in there? Well, you have 9. They're all not white. Out of how many marbles in the box? 9. 9 over 9 equals 1. So what is the probability you pull something from the box and it is not white? Probability is 1. It is certain to happen. Let's go ahead and do the next problem. A box contains 3 red, 4 green, 2 yellow. So here we go again. I'll be drawing this picture a lot. And maybe if I was thinking ahead, I would have drawn that out on every problem here. But it's funnier this way, I guess, to make people wait. Okay, here it is. You draw 1 marble from the box. What is the probability it is yellow given that it is not red? So this given that happens to denote conditional probability. And the shorthand for this, even though we don't have to write this, I'll write it anyway. What is the probability it is yellow? Given that, so there's the given that right there, it is not red. So let's go ahead and take care of the condition first. So the given statement is that it's not going to be red, so I go over to my sample space and I tweak it. I cross out all the reds. So now my box only has those 6 marbles in it. So what's the probability of pulling a yellow marble out of this box? Well, there are 2 yellow marbles out of 6 marbles. So 2/6 reduces to 1/3, and 1/3 is the answer. So that completes problem number 3. Okay, so now they're going to get a little more complicated. Problem number 4. We have the same setup with 3 reds, four greens, and 2 yellows. So we have those 9 marbles. You draw 3 marbles, one at a time, from the box with replacement. What is the probability you get 1 red marble and 2 yellow marbles in that order? So I'll just rephrase it here. 1 red marble, red, and then 2 yellow marbles, yellow, yellow. This is in that order. I just copied that down. And then this is with replacement. Okay, because we have the words, in that order, I can do this 1 probability at a time. So I'll put a smiley face there because it means that we can get this done with ease. Okay, so what is the probability you pull a red out of this box? Well, 3 out of 9. Now this is with replacement, so you put that red back in there. Okay, now what's the probability you pull a yellow out of that box? Well, there are 2 yellows and there are 9 marbles in the box, so this is 2/9. We multiply. Remember, in that order means we're dealing with permutations. Though you don't have to think of that right now. Okay. So after I pull that second marble out of the box and it's yellow, I put it back in because it says with replacement. What is the probability of pulling out a yellow now on the 3rd time? Well, 2 out of 9. So let's go ahead and see if we can cancel. I think we can. The 3/9 becomes 1/3. Nothing else cancels. So on the top I have 2 times 2 and then times 1. So I have a 4 on the top. And on the bottom I have 9 times 9, which I know is 81. I'll put that right there. Times 3. So I'm being a purist here. I'm doing all these calculations by hand here. 3 times 1 and then 3 times 8 is 24. So it looks like I have 243 on the bottom. So there's the answer to this probability question. Let's go ahead and do the next one, problem number 5, and it looks almost identical. The only thing that's going to be different with problem number 5 is this word right here. It's going to say without. So let's take a look at that. So there it is. You see the without. 3 reds, 4 greens, 2 yellows. looks like that. The probability of getting red, yellow, yellow, in that order. And then this is without replacement. It's going to be a little different, especially with the second two, or the last two fractions that I have here. In that order, it's good. It means I can do it one fraction at a time, so I put my happy face there. And it kind of starts off like the last problem. What is the probability I pull a red out of the box? Well, that is 3/9. Now here's the deal. This is without replacement, so when you pull a red out, it's going to look like that. And there will not be 9 marbles in the box now, but there will be 8. So now we go to the second thing. What is the probability of pulling a yellow out of this box? Well, there are 2 yellow marbles out of 8 marbles. Okay, this is without replacement, so now I'm going to cross out one of the yellows. And basically what I have now is I pulled a red out, and then I pulled a yellow out. And I'm keeping them out. So what is the probability you pull a yellow out of this box? We're working on this third one right here. And it would be 1 out of 7. Well, now let's see if we can reduce any fractions here. The 3/9 becomes 1/3. The 2/8 becomes 1/4. So on the top it looks like I just have 1 times 1 times 1, which is 1. On the bottom I have 3 times 4 times 7. 3 times 4 is 12. 12 times 7, I'll go ahead and do that over here. So there's 14 and 7, 8. So it looks like I'm getting 84 for the denominator. And so 1 over 84 is the answer for problem number 5. Let's go ahead and do the next problem. So the box contains 3 reds, 4 greens, and 2 yellows. We have these marbles in the box, 9 marbles. You draw 3 marbles one at a time from the box without replacement. What is the probability that you get 1 red marble and 2 green marbles, not necessarily in that order? So let me go ahead and just write the shorthand here. The probability of getting 1 red marble and 2 green marbles, and this is not necessarily in that order. So because I'm lazy, I'm going to write N-N-I-T-O, nanito, and then this is without replacement. And I'll abbreviate without like that, without replacement. So there it is. This is a little different from the last problem. In the fact, the last problem I was actually pulling some yellows out, and this time I have greens here. But this, not necessarily in that order, means that order doesn't matter in how I pull these out. So I could pull out a green, red, and a green, and that's good. We don't like these ones as much, so I'm going to put a neutral face. We don't like them because we can't just go one probability at a time. And if it's not necessarily in that order, and order doesn't matter, it makes it a combination. Combination without replacement or without repetition. So this is how we do the problems. I always do the denominator first. And I say, well, I'm just pulling 3 marbles out of this box. How many ways can I do that using combinations? Well, there are 9. Choose 3. Okay, because I'm choosing 3 marbles. 9, choose 3. So the bottom is anything that can happen. Now the top happens to be what I want. I want to choose 1 red marble from 3 red marbles. So using choose talk or combination talk, we would go, here's the reds, 3, choose 1. I'm going to multiply that by, now I'm going to take care of the greens. There's 4 greens in the box and I want to choose 2. So this is going to be 4, choose 2. So I know we can go and do the formulas for those combinations, but we could also use Pascal's triangle. 3, choose 1, we go to row 3, we move over 1, it is 3. So that first one right there is 3. 4, choose 2, I go to row 4 on Pascal's triangle and move over 2. So it's 6. 9, choose 3, I go to row 9 on Pascal's triangle and move over 3. 1, 2, 3, 84. Okay, now I'll try to reduce these things if I can. Let's see, I think 6 does go into 84 nicely. If it doesn't, then I will be embarrassed over here, won't I? So, we're doing some long division. Oh, look at this, 6 goes into 24 4 times. Okay, so perfect. So we know 6 goes into 84 14 times, and 6 goes into 6 1 time. The 3 and the 14 are not going to reduce, so it looks like I'm getting 3 over 14 for my answer. Yeah, this is why we have a neutral face, because well, this is not as easy as multiplying 3 fractions together. But this is how you do, not necessarily in that order, without replacement. And you'll never get one that says not necessarily in that order with replacement, because we never covered in this class combinations where repetitions were allowed. We may have done it as an extra credit problem, but we never did it as a normal problem. Let's go ahead and do some more problems from the review. And remember, your test is going to kind of mimic sort of what's happening in the review. You do your homework to build confidence. The review is to just see some different problems, and then the test is not designed to trick you. It's just designed so you do some similar problems. If you've done your homework, you should do all right. Box contains 3 red marbles, 4 green marbles, and 2 yellow marbles. So there they are. I've been drawing this pretty much on every problem. You draw 2 marbles one at a time from the box with replacement. What is the probability that you get 2 red marbles? And this is with replacement. Now, it never told me whether order matters or not. But as we discussed in the lecture, when it's just the same color, you can do it either way. And how I'm going to do it is the easier way, where I'm going to think order matters, and I'll do this 1 fraction at a time. And that's because it has the same color here. You know, in the other problems, 6 and 5 and 4, they were different colors that I was trying to pull out. So let's go ahead and do this. This is with replacement. What is the probability I pull a red out of that box? The probability of pulling a red out of that box is 3 over 9. I pull the red out, but because it says with replacement, I put the red back in. So what's the probability of pulling out a red, this is the second time, from this box? Well, it would be 3 out of 9. So this is with replacement. We're doing this in that order. Lots of statistics teachers would say these are independent events. That's cute, but we don't really need to use that vocabulary now. We can get the problem done without that. So this is 1/3 times 1/3. So 1 times 1 is 1 on the top, and on the bottom 3 times 3 is 9. So our final answer is 1/9. Okay, so our next problem. Now I'm doing this on purpose here. You draw 2 marbles one at a time from the box with replacement. What is the probability that you don't get 2 red marbles? Okay, so what do we notice about this right here? You get 2 red marbles, and this one right here, you don't get 2 red marbles. What you hopefully notice is that those are negations. This is the negation of that statement there. You get 2 red marbles, you do not get 2 red marbles. So this problem right here is complementary probability. And because we did the last problem, we should be able to do this problem pretty quickly. So you might wonder, well, what do you mean? Look at this. Okay. So we are doing the probability don't get 2 red marbles. And the complementary event, I don't have my blue pen, so I'll just use a purple pen. You do get 2 red marbles, or you get 2 red marbles. Notice this says with replacement, and that's with replacement, so those are the same, and that's important that we see that. So we've already done this problem. The probability you get 2 red marbles, that answer was 1/9. So I'm going to put that right here, 1/9. This problem is a tougher problem. You don't get 2 red marbles. Well, we now know what to do because these are complementary events, so I'm going to put the complementary probability. How do I calculate that? I go 1 minus 1/9. And remember, the quick way of doing that is to just go 9 minus 1 is 8. 8/9 is the answer to this problem. So this was a surprise because it says complementary probability, but it never really said complementary probability. So on the exam, I think what I'll do is if I give you a problem that involves complementary probability, I will label the problem complementary probability problem, just so you'll know. So that's what I'll do if it's going to be something this involved. And they'll probably be the last few problems on the exam. So there it is. Let's go ahead and do one more problem that involves this box of marbles. And as you can see, the sun is shifting. So there's some sun right there. So what I'm going to do is I'm going to adjust the curtain so it's not putting the little sun on the piece of paper. Okay, we have our box here that has 3 red marbles, 4 green marbles, and 2 yellow marbles. You keep drawing marbles out of the box, one at a time with replacement, until you get a green or a yellow. What is the probability that you end up with a green? So this is quite an experiment here. You're trying to end up with a green. But this experiment has different outcomes that can happen. I mean, you can get red, 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 yellow, and then it's done and you lose. Or you can get red, red, green, and then it's done and you win. So this is a rather complicated problem. And it's also related to the game of craps. And so what we did in the notes is we said, well, the last thing that you draw is going to come from this little box here. Because by the nature of the experiment, you'll never draw a red for your last marble. So your last marble will be one of these 6 marbles. So if you wanted to write this using conditional probability, you would say, what's the probability of getting a green given that the last marble you pick will be a green or a yellow? Okay, so really, what's the probability you pull a green out of that purple box there? Well, it looks like it's going to be 4 greens out of 6 marbles. 4/6 reduces to 2/3. And 2/3 is the answer there. So that is how you do problem number 9. Let's go ahead and look at problem number 10. Finally, we're getting away from the marbles, and we're talking about playing cards. A single card is drawn from a deck of 52 playing cards. What is the probability of obtaining a king given that the card is not 4? So the probability of getting a king given that the card is not 4. Okay, so what I'm going to do is take out my cards here. So that's what it looks like. You have a conditional probability here. We know that because it says given that, which I replaced with a line, and we do our condition first. So given that, you're not going to pull a 4 out of this box. So what does that mean I should do to tweak the sample space? I get rid of the 4s. So instead of having 52 marbles in the box, we need to go 52 minus 4, or just count the ones, and you'll have 48 marbles. So you are now pulling out of a box of 48 marbles or cards. What is the probability of getting a king? Well, how many kings do we have here? We have 1, 2, 3, 4. 4 out of 48. So we could try to reduce that. 4 goes into 48. I think it goes 12 times. 4 goes into itself 1 time. So this is 1/12. And we used the playing cards sample space here. So I'll go ahead and label this as number 10. And that will go with the PDFs. That's how you do a problem like that. So let's move on to problem number 11. You toss a dime, a nickel, and a penny. Find this probability at most 1 head. Okay. So what I'm going to do is I'm going to say dime, nickel, penny. And I'm going to realize that they can all land on heads. And we discussed in the lecture that, you know, since you have a dime, a nickel, and a penny, there's 2 things that can happen here, and 2 things that can happen here, and 2 things that can happen here. You multiply those all together, there's going to be 8 marbles in this box, with this marble right here being your first marble. So we also discussed that this probably reminds us of a truth table. And so I'm going to go ahead and just think of this as a truth table where I alternate the last column by 1. So head, tail, head, tail, head, tail, head, tail. I alternate the second one by 2s. So head, head, tail, tail, head, head, tail, tail. And then the first column I alternate by 4s. So 4 heads and 4 tails. So I will circle each of the 8 marbles. They are smushed marbles. And so this is what the box looks like. Now, are there other ways to do these probability problems? Absolutely. And we discussed some of the ways in lecture, like conditional probability, which is not this problem. There's a more complicated formula, but I'm trying to show you guys the easiest way to do these problems in order to pass the class, I guess. Okay, so now we go like this. Find the probability that you get at most 1 head. What does at most 1 head mean? At most 1 head means 1 head or less. So 1 head or less. So here's 0 heads, I'll put a check mark there. Here's 1 head, 1 head. So 1 head or less. So we cannot put a check mark near the 2 heads because it has to be 1 head or less. Here's 1 head, and then there's 2 heads, 2 heads, 3 heads. So it looks like I have 4 check marks. So there's 4 things in the box that I want. And how many marbles do we have in the box? Well, it looks like there's 8. 4 out of 8, which is 1/2. So this is the easiest way to do a problem like this. In a statistics class, they might bring up combinations, but you really don't need to do all that stuff for just 3 coins. Now, if you have 20 coins, yeah, then you take out the big machinery, but this is good enough. Let's go ahead and do the next 2 examples, which will be shown right here. You roll a pair of dice. Okay. So this is something you should know how to do for this test. You should know how to write out a sample space for a pair of dice. Now with a pair of dice, here's the first die and here's the second die. 6 things can happen with the first die, and 6 things can happen with the second die. 6 times 6 is 36 marbles. Now I'm going to draw this all out. Now when it comes to throwing 3 dice, I would not draw it all out, and I would use some counting techniques, but this will be the best for these 2 problems. So if you remember correctly, first die can land on 1, the second die can land on 1. The first die can land on 1, the second die can land on 2. First die can land on 1, the second die can land on 3, etc. So there's 6 marbles right there. And then the first die can land on 2, the second die can land on 1. The first die can land on 2, the second die can land on 2, etc. And then we continue. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and then we have our 6 column, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. If you count them all, there's 36 marbles. I'm not going to circle each of the marbles, but we'll use this to answer these two problems where you're rolling a pair of dice in each of these problems. What is the probability that the sum is 8? Well, the sum being 8 would be you add them up and you would get an 8, and so it would look like right here, 2 and a 6. That gives you a sum of 8, 3 and a 5, 4 and a 4, 5 and a 3, 6 and a 2. And it goes up that diagonal, and it looks like I've circled 5 of those. So we're going to put 5 for the top of the fraction, and there are 36 marbles in there. So 36 for the bottom. And there it is. Problem number 13, you roll a pair of dice. Find the probability the sum is 6, given that neither die came up 4. So here's the condition. Neither die came up 4. I've got to tweak the sample space. I have to get rid of all the marbles that have a 4 written on them, because that's what that means. Neither die came up 4. So I'm going to get rid of that column because that has 4s, and then this row right here. Okay, so what is the probability that the sum is 6? Well, sum being 6 would be the 1 and 5, the 2 and the 4, but that's not in the box anymore. 3 and 3, 5 and 1, along this diagonal right here. So there are 3 marbles in the box that have the sum of 6. I'm not going to put 36 on the bottom because those purple marks right there, those are not in the box anymore. So you can count the marbles that are not crossed out, or you can go 36 minus 11 if you'd like. So both ways would get you 25 marbles that are in the box still. So 3 over 25, this right here is conditional probability because a condition was given. And that's how you do problems 12 and 13. Let's go ahead and do some more problems. Problems 14 and 15, I put them together because they have the same experiment. You're going to roll a die and toss a coin. Okay, so when you roll a die, you have 1 through 6. So you have a die here, and then you have a coin. And the coin's going to give you heads or tails. So 6 things can happen with the die. 2 things can happen with the coin. So 6 times 2 is 12 marbles. So let's go ahead and list them all. So the die can land, so it's the same thing for both 14 and 15. The die can land on 1. The coin can land heads. The die can land 1. The coin can land tails. Okay. Now the die can land 2. And the coin can land heads. And then you can do 2 tails. 3 heads. 3 tails. 4 and then heads. And then 4 and then tails. 5 heads, 5, then tails, and then 6 heads, 6 tails. It's almost like you're rolling a 6-sided die here and then a 2-sided die there, which, I don't know, maybe some of you have a hard time imagining, or maybe have a hard time with me labeling a coin a 2-sided die. But that's kind of what we're doing here. So there are your 12 marbles. You can count them all. And it says in the first problem, what is the probability that the die shows a 6 and the coin lands head up? Okay, so 6, the coin lands head up. So notice the word here, and. And means you have to have a 6 and a head. And a lot of you could have done this without circling what I just circled there. So the only one that's a 6 in the head is this guy right here. There's only one marble that fits this description. And the answer for problem number 14 will be 1 out of 12. Now problem number 15, it's almost identical except we have the or, which means they're asking what is the probability the die shows a 6 or the coin lands head up, and this is the inclusive or. So 2 heads would fit this description because you landed heads. So now you've got to count all the things that are heads and all the things that are 6s without counting this one twice. So you have 1, 2, 3, 4, 5, 6, 7. So the answer to problem number 15 is 7 over 12. And remember that the or is the union and the and is the intersection. So this all goes back to what we first did in this class with set theory. Let's go ahead and do another problem. Number 16. The spinner problems. Alice spins the spinner on the left. Bob spins the spinner on the right. What is the probability that Alice spins a larger number than Bob? Well, how many things can happen when Alice spins her spinner? 4 things. How many things can happen when Bob spins his spinner? 3 things. Okay. And you know, we were putting slots there before when we were doing counting. So you go 4 times 3. That's going to give me 12 marbles in the box. It's kind of like in the last few problems we had 12 marbles in the box. So we're going to have 12 marbles here. And how I'm going to draw the box, I'll draw the box right over here. I'm going to say Alice can get a 1 and Bob can get a 2. So the first number will represent Alice's number. Alice can get a 1, Bob can get a 4. Alice can get a 1, Bob can get a 7. Okay, now Alice can get a 4, Bob gets a 2. Alice gets a 4, Bob gets a 4. Alice gets a 4, Bob gets a 7. Okay. Then Alice can get a 5, so we have 5, 2, 5, 4, 5, 7. And then the last one is Alice getting an 8. So 8, Bob gets a 2, 8, Bob gets a 4, and then 8, Bob gets a 7. So 8, 2, 8, 4, 8, 7. So you can pretty much throw those spinners away, and the game could just be drawing one of these marbles, because there are 12 marbles, out of that box. And then that determines who wins the game. So the probability that doesn't say Alice, does it? Let me get my white out here. Okay. Alice spins larger number. Okay, so let's go ahead and do this. Which ones have, Alice is represented by the first number, which ones have a larger number? Well, 1, 2, 1, 4, 1, 7, nothing from the first column. 2, 4, sorry, that's not 2, 4, that's a 4, 2. 4, 2, yes, so the first number is bigger. 4, 4, well, the first number is not larger than the second number, they're the same, so we're just not going to take that. And 4, 7 is not included in what we want. We are circling in orange what we want. 5, 2, yes, Alice has a larger number. 5, 4, Alice has a larger number. 5, 7, nope. But these guys right here, 8, 2, 8, 4, 8, 7, the first number is larger, so I'm going to circle those. So for problem number 16, Alice spins a larger number. Well, there are 6 things that we want from that box. Out of, there are 12 marbles in the box. 6 over 12 becomes 1/2. And that answers problem number 16. Let's go ahead and do problem number 17. Problem number 17. You spin the spinner twice. What is the probability that one or both spins come up 4 given that the sum of both spins is not 6? Wow. So this one seems pretty complicated. You're going to spin this twice. So what I'm going to do is think of this as like rolling a pair of dice twice, except these dice, each die has just 4 sides. 1, 2, 3, 4. And so the first time I spin, I can get a 1. And the second time I spin, I can get a 1. So 1, 1. First time I spin, I can get a 1. Second time I spin, I can get a 2. 1, 2. 1, 3. 1, 4. I'm not going to write a 1, 5 and a 1, 6 because this only has 1 through 4. So now the first time I spin, I can get a 2. And the second time I spin, I can get a 1. And then 2, 2, 2, 3, 2, 4. And then the first time I spin, I can get a 3. 3, 1, 3, 2, 3, 3, 3, 4. And then finally, I can spin a 4 first. And I can do 4, 1, 4, 2, 4, 3, 4, 4. So there's my box. It looks like it has 16 marbles, and we could have figured that out by saying 4 things can happen the first time, and 4 things can happen the second time, which gives me 4 times 4. I'm reaching for something over here. Where is it? Here it is. So when I rolled a pair of dice, I kind of had this same thing here. This right here, this little 4x4 grid is right here. It's right there. So it's part of the sample space for this, but this one just has 4 numbers each time, so it's not the whole thing. What is the probability that one or both numbers are 4, given that, so this is conditional probability, The sum of both spins is not 6. So, sum is not 6. So here is the condition. The sum is not 6. This one gives me a sum of 8. So that fits the description. Sum is not 6. These two here give me a sum of 7. These guys right here, these are the ones that give me a sum of 6. So the condition which I go to first in each of these problems, and I tweak the sample space to fulfill this condition. It says sum is not 6, so we have to cross out the marbles that have sum 6. And notice this diagonal here has sum 5. I guess I will circle them all now. Sum 4 is right there, sum 3, and sum 2. And when I'm saying sum, I mean S-U-M. Okay, so we've tweaked the sample space. And now we only have not 16 marbles, we have 13 marbles in this sample space. So that's going to be the denominator. And now let's go ahead and look at this. One or both numbers are 4. Okay, so what are both numbers are 4 right there. So anywhere you see a 4, that's what you want. So it looks like what I want in the box happens to be 1, 2, 3, 4, 5 different things that I would be happy to get. Notice the purple things that I crossed out, they came out of the box. They're not in the box anymore. So 5 over 13 is the answer to this problem. Let's continue to do more probability problems. 5,000 tickets were sold to raffle off a family pass to an amusement park. The Fishers bought 10 raffle tickets. What is the probability that they win the pass? Okay, so here's the deal. I'm not even going to draw all the things in this box, but there are 5,000. Marbles in the box. Now, 10 of those marbles have Fisher written on them. So let me just say this. There are 10 Fisher marbles. What is the probability they win the pass? So they're going to pull one marble out of the box. It's going to be 10 out of 5,000. Now you could, or you should actually, reduce the fraction, but you could do that by crossing a 0 off of each of those. And it looks like my final answer is going to be 1 over 500. So that is the answer to problem number 18. I think we classified these problems as miscellaneous problems. Let's go ahead and do this one. A class has 25 females and 10 males. If a person from the class is selected at random, what is the probability that the person is female? So the probability the person is female. Well, how many females are in that box? There are 25. And how many marbles do we have in the box total? Well, looks like 35. We should reduce the fraction. I think 5 goes into both of those. 5 goes into 25 5 times. 5 goes into 35 7 times. So it looks like my final answer for problem number 19 is going to be 5 over 7. Let's continue. A piggy bank. So notice what I'm doing on these problems. I guess I should show you. Each time I have a problem like this, I go ahead and draw out a box and convert all these problems to marbles in a box. So, I mean, 25 marbles that have F on them and 10 marbles that have an M on them. And then over here we had 10 Fisher marbles. That's what I'm doing on a lot of these problems. A piggy bank has 42 pennies. So once again, here's the box. 42 purple marbles, pennies, 8 nickels, 12 dimes, and 5 quarters. So that's what the box has. So there's a lot of coins in this box, or you can actually figure this out. This is 10, 17, carry the 1, 4, 5, 6. So it looks like there's 67 marbles. Hopefully I did the math correctly on that. Okay. Coin is selected, randomly selected from the piggy bank. What is the probability that the coin is a dime, given that the coin is not a quarter? Okay, so let's go to our condition. It's not a quarter. What does that mean you do with the quarters? You cross them out. Tweak your sample space. Do your condition first. And now we're just doing the probability of pulling a dime out of this box. And it doesn't have 67 marbles anymore. It has 62, since you took 5 of the coins out, the 5 quarters. So it looks like we have 62 on the bottom, and on the top you're trying to pull out a dime. Looks like it's going to be 12 over 62. I think 2 goes into both of those. 2 goes into 12 6 times. 2 goes into 62 31 times. So my final answer is 6 over 31. This is another one of those miscellaneous problems, but this one happened to turn into conditional probability, and look, we see that because there's a given that. Let's continue with more of these miscellaneous type problems. A box contains 8 light bulbs. 3 are defective. So why don't we go ahead and draw that box? So the defective ones I'll just call bad, okay? So you have 3 bad light bulbs, which means probably the other ones are good. So I'll label those G. And I'm not going to put 8 G's because 8 is the total number. I'm going to put 5. Good, 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 good. So if you count them all, you count up 8 marbles in this box. 5 are green, 3 are blue. If 2 bulbs are randomly selected from the box, find the probability that both are defective. So we are trying to find the probability of getting a bad and a bad. Okay, since it's the same color, saying order matters or not necessarily in that order. It doesn't matter which one we say. So I'll just say order matters. Is this with or without replacement? And this is what we have to figure out on this. Well, if you're grabbing 2 light bulbs from this box, I mean, if you think about grabbing one and then grabbing another, you're definitely doing this without replacement. Like if someone says, hey, grab me 2 light bulbs from the box, and then you grab one, and then you put it back, and then you mix them around and grab another and bring that last one to that person, they'll say, hey, what's up with that? I asked for 2 light bulbs. You actually have to grab one and then grab another. You're doing this without replacement. Okay, so we can do this one fraction at a time because it's the same color. What is the probability of pulling a bad or a blue out of that box? Well, it would be 3 out of 8. So we're going to go ahead and, this is without replacement, we'll cross out one of those. What is the probability of pulling out another bad or another blue? Well, 2 out of 7. Does anything cancel? Yeah, the 2 and the 8 do. So 2 goes into itself 1 time, 2 goes into 8 4 times. Nothing else cancels with the 3 on the top. So it looks like my final answer is going to be 3 over 28. And there it is. Let's go ahead and do this grocery store problem. A grocery store has 12 cartons of milk and 6 are expired. So like in the last problem we talked about light bulbs, and now we're talking about milk and expired milk. But don't you see, in some ways, if we model it with marbles in a box, we're kind of doing the same thing every time. Of course, you know, replacement might change or whatever, but let's go ahead and model this. 7 of those cartons of milk are expired. You might say that 7 of them are bad. So 1, 2, 3, 4, 5, 6, 7. How many are good? Well, there were 12 cartons of milk, so you're not going to put 12 goods. There's only going to be the 7 plus something equals 12. It's going to be 5. 1, 2, 3, 4, 5. 3 customers buy milk. What is the probability that the first customer gets expired milk, the second customer gets non-expired milk, and the third customer gets expired milk? So basically what they want to know is this is what's going to happen. The first customer gets expired milk, that's bad milk. Second customer gets non-expired milk, that's good milk. And the third customer gets expired milk, that's bad milk. Some of you would have preferred to use E's for that, but we just went ahead and put B's there. Okay, so the deal is, there seemed to be an order on here. In fact, order does matter. First one gets this, second one gets this, so this is in that order. Now, what can you tell me about replacement on this? Well, this is going to be without replacement. Why? Because the first person buys their carton of milk and they leave, so that carton is not there anymore. So this is in that order, which, you know, I mean, I didn't do this in the last one, but you put a happy face here because we can just do this one fraction at a time, multiplying 3 fractions together. So let's see if we can do this. What's the probability you pull a blue out of this box? Well, there are 7 blue or expired milks, and we have 12 marbles in the box. 7 over 12. Now, because it's without replacement, we cross out one of those. It's not there anymore, and now you want to pull out a G. How many G's do you have in the box? You have 5 G's out of 11. So now you pull one of those out. That's the second customer. They buy it, they leave. And now the third one is a B. How many Bs do you have in the box? Well, it looks like there's 6 now out of 10 things in the box. Let's go ahead and have our canceling party. What cancels? The 5 and the 10. That becomes 1/2. The 6 and the 12 becomes 1/2. And you have a 7 on the top, which is not going to cancel with anything on the bottom. So problem number 22, you'll have 7, which is on the top, and then you have 2 times 2 times 11, which is going to be 4 times 11, 44 in the denominator. 7 over 44 is the final answer for problem number 22. Let's go ahead and do problem number 23. You roll a die 3 times. Okay, so right away, that's where I draw the line. I'm not going to draw 216 marbles in a box. I'm going to use counting techniques to do this. So I'm going to say I have a box here. 1, 2, 3, 4, 5, 6. I'm going to draw from this box 3 times. Of course, it's a die, so this is with replacement. So you roll a die 3 times is the same as drawing from this box 3 times with replacement. What is the probability that the first number is 1? Let's write this out. The first number is 1. The second number is even. And the third number is at most 4. Now, of course, this is going to be in that order because they said first, second, third, so this is in that order. Which we're happy about. And then it also says with replacement. I mean, that's what's implied from the problem because you're rolling a die, it can land on a 5 more than 1 time, so this is with replacement. I haven't been very consistent with just going W with a slash and then spelling out with, but hopefully you haven't been thrown off by that. So we can do this one fraction at a time. What is the probability of pulling a 1 out of that box? It would be 1 out of 6. The probability of getting an even number. This is the second time we do this. An even number, there are 1, 2, 3 even numbers in there. So 3 out of 6. And then the probability of getting at most 4, which means 4 or less. That's what at most 4 means. So it would be 4, a 3, a 2, or a 1. That's at most 4. So that would be 4 out of 6. A statistics teacher would go on and on about how this is independent events, and that's cute. That does work. We don't have to say that here. I'm going to reduce any fractions that can reduce. So 1/2, 4/6 is 2/3. And we still have a little more reducing to do because we have a 2 up here, and you can either cancel it with the 6 or cancel it with that 2 there. I'll just cancel it with this 2 here. So those become 1s. So my final answer for this problem is 1 times 1 times 1. So I have 1 on the top, and on the bottom I have 6 times 1 times 3, which is 18. So my final answer is 1 over 18. And that is what it is. So we only have like a few more problems. I think 3 more problems on this review. With 24 not really being that long of a problem, these last 3 problems are labeled as complementary probability problems. So 24, 25, and 26 will be using complements. If the probability of rain is 1/5, then what is the probability I'll do it in a different color. I'll do it in purple. Of no rain. Well, rain and no rain, those are complementary events, so these are going to be complementary probabilities. And the way you get the complementary probability is by going 1 minus 1/5. Whenever you have a probability, whenever you have 1 minus a probability, you can just do it the quick way by going 5 minus 1 there, which is 4, and then you put it over 5. And we talked about that during the lecture on that. So there it is, 4/5 for that one. Let's go ahead and do another problem here. Roll a die 3 times. Now we did that in problem number 23, but now they're going to ask us a problem that is a little bit more complicated. So rolling a die 3 times. 1, 2, 3, 4, 5, 6. You're going to draw from this box 3 times with replacement. Okay? Because when you roll a die, it can land on the same number. That's why we say with replacement. What is the probability you roll a repeated number in the experiment? So the probability you have a repeat. This right here is a tough problem. And this is a complementary probability problem, so I'm going to go ahead and consider the complementary event. The complementary event of getting a repeat is getting no repeat. Of course, this might remind you of the birthday paradox that we did. So, no repeat. Let's go ahead and think about this. The first time we draw from this box, it could be anything. So the first fraction is going to say 6 out of 6. The next time, so suppose we ended up getting like 2. Well, if we don't want repeats, then the next time we do not want a 2. The probability of getting not a 2 here would be 5 out of 6. So suppose the next time we rolled a 6 or drew a 6 out of that box. Okay, so the third fraction is going to be a probability. And if we ended up getting a 2 and a 6 and we don't want repeats, then the probability of not getting a 2 or a 6 would be 4 out of 6. So we are computing the complementary probability. Let's go ahead and reduce anything that can be reduced. 6 over 6 is 1 over 1. 4 out of 6 is 2/3. And then this 2 here can cancel with this 6. So 2 goes into itself 1 time, 2 goes into 6 3 times. So on the top I have 1 times 5 times 1, which is 5. And on the bottom I have 1 times 3 times 3, which is 9. So if you're taking the test, a lot of people like to stop here because they're like, okay, that's enough, I'm tired. But go a little bit further, because this is not the answer, this is the complementary probability. To get our answer, we're going to go 1 minus 5/9. So I go 9 minus 5, which gives me a 4. 4/9 is the probability that I roll a repeated number in this experiment. And I didn't have to draw a sample space of 216 marbles. I was able to use counting techniques and the complementary probability. Let's go ahead and do the last problem from this chapter review, and then we'll look at the puzzles and we'll be done. Notice the experiment is the same. Roll a die 3 times. Now they're asking you to do something different. So let me go ahead and set up this right here. 1, 2, 3, 4, 5, 6. We are drawing from this box 3 times. This is with replacement. What is the probability you roll at least 1 3 in the experiment? So you get at least 1 3. Then that means you can get 1 3, 2 3s, or 3 3s. Now that's a tough problem. And it's kind of like Demir's problem, that gambler we talked about. And so we don't really want to do this problem. This is labeled as a complementary probability problem. So we're going to consider the complement. And I like to do the complement in a different color. So the complement of at least 1 3 would be no 3s. That covers all the other bases. So what's the probability you roll a die 3 times and you end up getting no 3s? Well, the first fraction is going to be, what's the probability of not getting a 3? It would be 5 out of 6. Okay, what's the probability of not getting a 3 the second time? 5 out of 6. What is the probability of not getting a 3 the third time? 5 out of 6. Nothing cancels. So 5 times 5 is 25. 25 times 5 is 125. 6 times 6 is 36. 36 times 6, 18, 19, 20, is 216. Okay, before you box that answer and say, okay, that's my answer, remember what you're doing. You're doing this problem, at least 1 3. So get rid of the purple pen, and I'm going to go like this. I'm going to go 1 minus that probability. That gives me the complementary probability. 1 minus 125 over 216. The quick way of doing that is to go 216 minus 125. So 6 minus 5 is 1. Once again, doing all this stuff without a calculator. 21 minus 12 is 9. So 91. So this gives me 91 over 216. So a very tough problem can be done using complementary probabilities. So let's go ahead and look at our puzzles. My very educated mother just sent us 9 pizzas. So look at this. M, B, E, M, J, S, U, N, P. What does that remind you of? That should remind you of the planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Now some of you say, oh, Pluto's not a planet. It's been declassified, but then it was classified. I don't know. So if you don't think Pluto is a planet, you can say, my very educated mother just sent us nothing. And that would satisfy those people who cannot accept that Pluto's a planet. Let's go ahead and take a look at homes. Well, this is a great way to remember the Great Lakes. So if you remember homes, then you can remember Huron, Ontario, Michigan, Erie, Superior. Okay. Before this, people would say, hey, what are the Great Lakes? And I'd probably get like 4 of them. Well, this one's kind of a dumb one, but I put it in here anyway. These are states bordering Mexico. California, Arizona. I think that's New Mexico, and then Texas. Okay? I'm no wimp. These are states bordering or touching the Great Lakes. And I'll let you figure them all out, you know, but this helps you go, oh yeah, you know, I mean, that W, Wisconsin, Pennsylvania, etc. Okay, so you can figure that out, but I'm no wimp gives you all of them. Now this one right here, Washington's Army jog, yada, 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 yada. Okay, so what's up with that? Look at this. W, A, Washington, Adams, Jefferson, etc. If you remember these two sentences, well, the first sentence, I believe, gives you the first 11 presidents, and then these letters here we actually have Hayes there, and Johnson. Clever, heart-shaped, I'm not taking that S there, and then Clay maps. Those give you the next 14 presidents. So this gives you the first, we'll just say first 25 presidents. Maybe you can add to this and bring it all the way up to modern days, but I mean, this is pretty good. I thought that was cool. So sometimes, I mean, you might be in an anatomy class or a biology class. There's lots of other things, little devices that you can use to learn things. Like I remember Farm B, fish, amphibians, reptiles, mammals, and birds. Those are your vertebrates. Keep pond clean or fish get sick, and that was like kingdom, phylum, class, order, family, genus, species. So there's lots of great ways out there to remember things for your other classes. Well, this is it. One more test to take for this class, and you are finished. So congratulations if you've made it this far. I would normally say I would see you in the next video. I may see you sometime when things get better. You guys have a good day. Study hard.